Hello students, in this lecture series wanted to introduce chapter 15, which is on sampling distributions. Now I kind of wanted to start off by kind of talking about a lot of the ideas we covered in chapters 1 through 9, as they're very important for establishing the math that we're going to be doing for the remaining chapters. And if I could summarize the kind of the main ideas that we're going to be working on in the next 2 weeks, it would be what's called statistical inference, which that idea is if we take a set of data from a population, if we take a sample from certain members of, say PLNU campus, we take 100 data points and we wanted to, the idea is how do we use that information to draw conclusions? The issue is we can look at data and make our own conclusions, but how do we use mathematical basis to really be certain about our conclusions? And how do we know and what level of certainty is an acceptable outcome? And that's, I think, the most difficult idea within statistical inference. And so we're going to learn the fundamentals so that you know how to properly do it, and so you're just not making conclusions that are unfounded. And I think that's one of the biggest issues that our society faces today when it comes to statistics. But to begin with, the idea of sampling distributions is what we're going to be studying in chapter 15. And it is very paramount to kind of understanding the key ideas in inference. And chapters 16 and 17 are on what we call confidence intervals and significance testing, which kind of put a lot of the circle back to definition we looked at last week. But it's the key difference between the term sample and population, and it's very paramount in for doing proper statistical inference to understand this difference. But just sort of remember, the population is what we're trying to study. Like, say, for example, the population could be the student body at PLNU, which, again, the population size would be, 2,000 to 3,000 students. Or, a different type of population similar to that would be population of all college students in America or all college students in the world. The population is sort of like, what do we care about? What are we studying? And the sample is the data that we take from that group. It should be a smaller, smaller sample than usually it's impractical to get information from literally everyone. And the goal is to take a subset of the larger group. And that's the key difference between a sample and a population. So now defining another term that is going to be used quite frequently. Sorry, my head's in the way here, but it says a parameter is the number that describes the population, whereas a statistic is a number computed from the sample data without making use of any unknown parameters. And this is just the definition in the book. Or to sort of summarize what this is saying is we refer to parameters as the details of the entire population. And statistics are something that we compute from our sample. And we are not making any assumptions. Basically, we're not allowed to make assumptions from the original population. We're kind of just taking the data, calculating from there. And basically, we already have studied the mathematics behind the key factors or the key statistics that we need for studying, starting with the normal distribution at least. So, when we were talking about a normal distribution, let me grab my highlighter real quick. And again, a normal distribution is like, we're making a density curve, which is describing the behavior of the entire population. And mu, the mean, is the average value of the entire population. And sigma, we call that as the standard deviation, which is a measure of the spread of the data. And basically, when, going forward, if you ever see the use of mu and sigma in any of the chapters, that's always referring to the population's mean and the population standard deviation. So, like, going back to the PLNU student body example, that would be, let's just say age. We're studying the age of PLNU students. Mu would be the average of all the students. And so sigma would be the standard deviation of all the students. And if if we're assuming it's a normal distribution, we could make inferences about that using normal distribution math. That's kind of one of the things we're going to elaborate into in the next couple chapters. However, so this is the key difference. X bar, as we learned back in chapter 2, stands for the average value, the mean value of the not of the population, but of the sample. It's like, right, if we have data, let's say we took data from 100 PLNU students, we calculate, okay, what's the average of the sample? And that's the only difference between these. They're the same idea, X bar and mu. You could think about them, they're the same conceptually. What is the mean value? X bar just refers to our sample, whereas mu refers to our population. And same thing for standard deviation. The standard deviation of our population as a whole would be sigma, whereas S or S sub x, two different notations that we've used so far, refer to the standard deviation of the sample. So again, it's like, say we have 100 data points, and we're trying to figure out what's the standard deviation. We went through that mathematics in chapter 2 as well. And we use the S sub x, remember, just means if we have more than one data set, we can specify what variable we're doing with the x subscript. But basically, how you can remember this is we use, English letters for the sample, and we use Greek letters for the population. And that's an easy way to make the distinction about which is which. And also to mention, the idea of statistical inference is to take the information that we have, right? We have 100 data points that we've collected from PLNU students. We can find the mean of that. We can find the standard deviation of that. And the goal is to make inferences about, okay, what about the entire population? Now, obviously, that's something we don't know. That's always the assumption, but we're trying to extract a level of information from the data that we've collected. And that's the key idea in chapter 16 and 17. And, if you ever see the terminology, a statistic is something that we calculate from our data, whereas a parameter is the actual real results of the population. Now, the thing about parameters is we don't often know what are the exact parameters, but we're trying to estimate those parameters, mu and sigma. And sometimes there's a lot of different methodology. That's kind of the thing that you have to work on in the next few chapters. Let's look at a quick example. It says that researchers surveyed 15,624 American high school students and found that 27.2% of those were in the 9th grade. It then says the percent of all American high school students who are in the 9th grade is approximately 27.5%. Then we're told that the percent of those surveyed who were in grade 9 and carried a gun to school was about 4.5%. So kind of we're faced with a lot of numbers here, and then we're asked to determine which percentages are parameters and which are statistics, and then to extract some information from this. So let me end the slideshow here, and that way I can go back to the notes, which I can write from my tablet. So give me just a sec to get this going. And we already covered some of this in earlier, but just to sort of, if you've printed out the notes and are trying to follow along, this is a key distinction. The mean of the sample is written as x bar, as we did in previous chapters, as the average of variable x. And when we're talking about the population as a whole, we refer to that as mu instead, something we typically don't know, and the goal is to use our x bar to try to make inferences about mu. And with standard deviation, same deal. We use S or S sub x, either way, for the standard deviation of our sample. And then to make inferences about the population as a whole, which we use sigma as the variable for the standard deviation of the entire population. And we refer to x bar and S as statistics, and mu and sigma as parameters. So now getting back to this example that we were just looking at, sorry, I got distracted trying to fill in the packet, but it asks us to determine which of these bold-faced percentages, which is a parameter and which is a statistic. So we had 3 different percentages. So the first one, 27.2%. So let's reread what that's describing. It said the researchers surveyed 15,000 American high school students and found that 27.2% of those surveyed were in grade 9. So the thing, if we're trying to determine whether that's a statistic or a parameter, so let's just go ahead and write down 27.2%, does it refer to the entire population or just from the data collected? It doesn't matter how many data points are in the sample. And so first thing we want to ask ourselves is, what is the population here? And basically it refers to, well, American high school students, and that's the answer to the question. Whoops, didn't mean to do that. What's our population? So basically, we would need to know data from every single American high school student to know the parameter. So this is a statistic because this is just of those surveyed. It's not the full group, and that's kind of the idea, right? Is we take a survey of some to get information about the whole, because often it's impractical or impossible to collect literally every data point from every single American high school student. for reasons. So yeah, this would be a statistic. And it would refer to as X bar, in this case, the average value. Or technically, this is a percentage, so we actually use a different notation, p hat. We're going to circle back to that notation later, so don't worry about that for now. But it still elicits the same idea. So next up, it says the percent of all American high school students who are in the 9th grade is 27.5%. So notice this one says all, literally the entire population. This sample was taken as part of those students. And basically, so this percentage would be our parameter as a whole. Notice that they are a little bit different, and that is very common. So this would be a parameter. And another way to remember this is statistics are generated from the sample, and parameters describe the population. And that key, that's the S and S, P and P, another way to help you remember those terms. And so the third percent we're told is the percent of those surveyed who were in the 9th grade and had carried a gun to school was 4.5%. So if we want to know, well, is that a parameter or a statistic? That would definitely be a statistic, because it said it was taken from the survey, right? That wasn't information. And how would we possibly know? Certain parameters would be impossible to know. In this case, we know the parameter for how many students are in the 9th grade in all of America, because we have that data, right? People officially enrolled in school. And, a lot of times your parameters are not perfect because there could be error in these, a collection of data from literally every student. But when we're taking our sample, it's pretty close, and this is what we generally expect. Is when you take a sample, it also depends on the sample size in terms of the accuracy of your data. But anyways, this would be, 4.5 would be a statistic because it was taken from the survey. And this sort of statistic, it would be impossible to know how many 9th graders carried a gun to school out of literally every one, because that data is much more complicated than just if you're in the 9th grade or not. Now, the last question it asks, or the second question, is how many 9th graders were in the sample, and how many carried a gun to school? So basically, if we take the sample as a whole, n is typically the variable we use for sample size. We had 15,624. And so if we wanted to make kind of a guesstimate of, how many students in our survey carried a gun to school, basically we could multiply the percentage by the sample size, right? Because from our statistic, we were told that 4.5% of those carried a gun to school. And we also know the total size. So, if we just multiply, so 15,624 by 0.045, the percentage in decimal form, right? Because we want to make sure to use it in decimal form. That would give us approximately 703 students carried a gun to school in our sample. And, rounding to the nearest whole because it's student size, it's the number of students. And so we could take information from our percentage and kind of extract that, knowing the sample size. Another thing is, what does this mean about the entire population of American high school students? So the population as a whole, notice that the percentages were relatively similar, and we'd expect, maybe the percentages of our entire population of 9th graders was also similar. However, notice one of the issues with this is we're not really told how the sample was obtained. And as we discussed, back in chapters 8 and 9, the methodology behind the sample can affect bias. So one thing you might think is, could we make a conclusion about all 9th graders and how many carried a gun to school? Like, let's say we want to know how many 9th graders in the entire U.S. carried a gun to school. Well, first of all, we need to know how many high school students are in America. Or 9th graders, rather. And this is something we're not told, so we can't really do this. But let's just say it was like 200,000. I don't know, I'm just making up a completely random number. I have no idea how many 9th graders are in the U.S. But let's just make up a number, 200,000. It's probably more than that. But anyways, one way you could figure this out is you could just look up, how many high schoolers are in the United States, and then divide that by 4. Not a perfect system, because you'd expect there to be less seniors than freshmen, because certain students don't finish high school. But again, I'm overthinking this. Let's try to get through the point I was trying to make. Let's just say there's 200,000 9th graders in the U.S. basically, well, we could multiply that by our statistical percentage, which was 0.045, to make a guesstimate for the entire population. What about the actual whole population? And say, okay, that would be close to 9,000 students that carried a gun to school, hypothetically. But the question is, what's the validity? So notice what I'm doing is called an inference. I'm taking my sample and trying to make an inference about this. And doing this is not good practice because, first of all, we don't really know if there's bias within the survey, right? Who was surveyed? Were these ninth graders that took the survey, were they all in the inner city? Or were they all in, suburbs? Those sort of factors can make a difference in the answers that we get, and those biases could create a poor distinction or a poor survey at the end of the day. And another idea that we discussed in the last couple chapters is randomness is better. So if this was from a simple random sample of American high school students, then we could probably do this more accurately than if there were bias. But also at the end of the day, 9,000 is a very specific number. It's still not very likely to be correct. Basically, what we should do more proper practice is to find a range of values that we think it could be within. Because again, trying to take a very specific sample and making implications about the whole is not exactly proper. But this is kind of the idea that we're exploring, and I wanted to sort of show you, okay, I have a sample and I'm trying to make an inference about the larger population.